Okay. So here's kind of the deal for today. So we're going to look at what we want to look at is orbital mechanics, right? So click everything closed here and let's have a look. So we've talked about the universal law of gravitation, and that is really what we need to do to study any interaction between any objects, but it gets complicated, right? In calculus, when we get to the point soon where we're doing anti-differentiation, which is the opposite of differentiation, it's called integration or anti-differentiation. We're going to get to a point where you'll be able to at least understand, you get a glimpse of kind of what you'd have to do to rigorously solve for an equation of motion for a bunch of bodies in orbit. And it gets pretty complicated if you have more than two, but it can be done. But we can simplify things too. If we make two very simple assumptions, and these are oftentimes not bad assumptions.
Would this be good to write down?
No, you don't need to.
Okay.
These will be up on the site. You don't need to write this down. I'll make sure the notes are updated, today or tomorrow for sure. So, assumptions. So a small mass, lowercase m, little m, orbits a much larger mass, capital M. This allows us to view the motion as if capital M, the big mass, were stationary. In fact, we can even look at it as if it's an inertial reference frame, right, where it's non-accelerating, okay, placed on M without any significant errors. Mass, this lowercase m, is the satellite of the larger object, big M. I don't know, that B snuck in there, that's not supposed to be there. If the orbit is gravitationally bound. Okay, so all this is saying is, in reality, like when the Earth revolves around the sun, is the sun stationary? No, it wiggles a little bit, right? And we'll look at, I want you to see that too, because that's actually an astronomical tool that we use, that we as scientists use to try to look for extra solar planets, right? When we want to look for planets around other stars, that's one of the means we have to determine if there's a planet there. Planets are really difficult to actually see around another star because they're so dim and the stars are so bright. But we have some ways of finding them that are pretty ingenious. They really are pretty easy to understand. Yeah.
So the sun, orbits just barely?
It wiggles around a little bit in response to the tug of the planets.
Does it also rotate then?
The sun, I don't know. I'm assuming the sun must rotate a little bit. But I don't actually know the answer to that. I probably have, and I just have forgotten. I don't know. I would guess that it would rotate a little bit. Yeah. Because it's going to be, I would guess that it's going to maintain some of the initial angular momentum when the solar system was formed. It was just a swirling disk, and so the sun, I would imagine, probably must rotate a little bit. Yeah. So that's one assumption, that the big mass is really big and the small mass is really small. Good assumption. The mass of the Earth, for example, is so much smaller than the mass of the sun as to be trivial. Okay. And then the other thing is, and this isn't a big deal, the system is isolated from other masses, right? So and that's pretty good. I mean, if you're talking about a solar system, the other stars are so far away that they don't really exert any recognizable force on the planets in the solar system, right? So everything else is outside and we can neglect it. Okay, so then if we do that, we can come up with, and it's been done by Kepler, and he actually, some of the stuff he arguably stole from others, but he assembled it all. He gave us three laws, Kepler's laws. First one, the paths of all the planets or satellites are ellipses with the sun or whatever's the gravitational center at one focus. Yes, sir?
If the Earth was the size of the sun, would it be habitable?
No, it wouldn't. No, there's a certain upper limit. And there's all kinds of reasons for that, but one of them is that the gravitational force would get so strong that it would cause problems with the atmosphere, for one thing. So yeah, there is an upper limit, but above a certain level, you would have a star anyway. You wouldn't have a planet above a certain limit. So let me pull up a little demo of this. I've got a bunch of stuff on the physics page, which is kind of fun to mess with. So if we go to, let's see, where's physics? There's physics here. Pull up. There's physics. So if you go to Unit 4, I've added a bunch of kind of fun stuff down here. If I like the interactogram. This is a good one just for the purposes of this. So you can see there that a planet moving around a star describes the shape of an ellipse. Okay? And if you want to make it more or less eccentric, the ellipse, we can do that. See, I think we can go to, well.
What does it mean by out of focus?
Oh man, I gotta, oops, that's not gonna work very well. If you, how come I reset, there we go, okay. At a focus, okay, so here's what that means, I'll explain that to you. So, let's say we got a planet, and I'm gonna start it off with, how about just like that, just a tiny bit of speed. That's going to be a highly eccentric ellipse. It's not going to be circular at all, right? Oops, wasn't even enough of an ellipse. Let's make it just a little bit more. And then, I don't know, it's not looking good either, but we'll see. Oh! These are really fun to play with. I spent my whole lunch period just playing with these things. I think this is just barely going to make it. So that's a pretty eccentric ellipse, right? What's that mean, eccentric ellipse? You guys talk about ellipses in pre-calc?
Not really.
Okay, so an ellipse is when it's very squashed. It's eccentric, yeah. A circle is an ellipse where both foci, can I pause this? Yeah. So when you draw an ellipse, this is kind of interesting. You have two foci. So there's one and there's one. Individual, singular would be focus, right? So at one focus, that's going to be the center of mass of the sun, for example, right? The gravitational center. When you want to draw the shape of an ellipse, one way to do this is to put two nails
and then have
on board.
String.
Yeah, and you have a loop of string, and when you pull it tight and you move a pencil around so the string is always tight, it's going to make this shape. So for example, right there, the string would look like this. The string would look like, right? And then if I go over here a little bit, like right there, for example, now the string would look like this. It'd be wrapped around, oops. How do I do that? It'd be wrapped around,
Focus. I remember.
right, the two nails like that. But the length of the total length of the loop is always the same, right? And that's an easy way to create an ellipse. See, understand what I'm saying with that? Okay. Okay, so that's Newton's first law.
Kepler.
Or Kepler's first law, sorry. Kepler's first law.
If that simulation, I guess, resembled Earth's orbit, correct?
Yes, right.
So then, I noticed it got a lot faster when it went around.
Right, okay, we'll get to that in just a second. So that's Kepler's second law.
Okay.
So the first law tells us that the paths of the planets, or any satellite orbiting a gravitational center, it describes an elliptical orbit, right? And one other thing I was going to mention. So what happens if we want to make this more circular then? What's going to happen to the foci?
They're going to get closer together.
You get closer together, right? And if we want to tweak this orbit just a little bit, that's a pretty eccentric one where the foci are very far apart, right? Compared to, and we call this the major axis, has to do with the long dimension of the ellipse. If the distance between the foci is similar to, is very close to the major axis, then it's very elliptical. Okay, but if we do something instead, like, let's say like this. So if I start with a planet, let's just try that. I don't know if that's a lot more circular. It's still going to be elliptical, right? Okay, but notice what happens now, that instead of the foci being way out here, they've moved in a little bit, and so they're closer to the center. And as they move in more and more, this is going to become less eccentric, and it becomes a circle when they overlap in the exact center. Okay, make sense? All right, so there's Newton's second law, or Newton, Kepler's first law. Okay, Kepler's second law says that okay, this is kind of interesting. An imaginary line from the sun to a planet sweeps out equal areas in equal time intervals. Okay, so we'll go back to this last simulation,
Back to that.
and look what happens now if we I turn on, try that. If I turn on Kepler's second law, those are equal time intervals. What do you think is true about each of those sectors?
They're reflected.
Equal area. Yeah, right? And so what does that imply about the speed of the satellite when it's very far away? It's much slower, right? In order to get the same area, it's moving much more slowly over here. Okay? Make sense? There's another way, it's kind of nice to visualize that.
Why don't we feel that somehow?
Say that again?
Like when the Earth whips around the sun, I guess
Well,
to say.
ours is pretty.
Pretty circular. It's almost a perfect circle, yeah. But comets would be a good example of satellites with highly elliptical orbits, right? Like Halley's Comet only comes once every, 88 years or something crazy like that. And so when it comes by the sun, it's going really fast. It doesn't stay in the solar system very long. But then when it whips out far away into the, into the Oort cloud, it's so far away, it's moving so slowly that it takes a long, long time to get back. But once it's here, it goes pretty quickly, right? I got another, let's go to this other simulator. I think, well, this is maybe that was a good one too. They're all pretty good, but.
Are there any planets in our solar system that don't have particularly circular?
Oh yeah. The most circular, I believe, is Venus. And I mean, I know it doesn't really count, but Pluto's is highly elliptical. It was very, very eccentric. Well, yeah, it's a dwarf planet. The rest of them are pretty circular. And you know that what's probably the biggest, they're just trying to suck us in, get us all excited, so I'll subscribe to this for $250 a year, but not happening. This is really the best one. Look at how it shows the areas. This is pretty cool. That's a pretty cool,
That's a circular orbit.
it's a pretty circular orbit, yeah. We can increase, but here, we can mess with the eccentricity and make it much more. Right? There you get an idea. Okay, so there's a good visualization of Kepler's second law. Okay? Now Kepler's third law is the only one that's quantitative. How do I pause this? One more, what's one of these planets? Oh, there you go. Okay, so there's Venus.
I think it just changes the shape.
It changes the shape, and I think it changes, well, look at one astronomical unit is the distance the Earth is from the sun. So it gives you an idea, where we are with respect to Venus. Let's look at Earth. Let's add Earth. Earth, so look at the eccentricity, 0.02. That's pretty circular,
What was
right?
Venus?
0. Same, to 2 places.
What about Mars?
Mars is a little bit more. No, a little less, sorry. Thought it was a little more.
So Pluto is the weird,
Yeah, Pluto's
weirdest.
1.25. That's pretty high. Look at 1 AU on this scale. See it down there? That's the distance between those 2 lines is the distance between the Earth and the Sun. So Pluto, you can see, it gets out there a long ways.
Each one of those is 5 years.
Each one of
I think
those
that's
is,
what that-
yep,
that's
5
right.
years, yeah. So when it gets way out here, it's not moving very fast, is it?
What's the furthest thing?
Actually, it's still moving pretty
solar
fast.
system?
Furthest, well, there are some dwarf planets that are really far away, and there's some speculation now. They call it Planet X. There's a planet, possibly a decent-sized planet that's really far out there that they're speculating about and studying right now.
Trying to find it. Mars.
Yeah. Yeah.
How far out can it get before it just kind of leaves the gravitational?
Well, they could get arbitrarily far as long as the velocity is really low. If you started to get half the way to another star, then you get competing effects from different gravitational centers. But stars are pretty far. So,
Can you have a planet going in between 2 stars?
funny you should ask that. Yes, you can, and we'll get there. Okay, so let's go back here then. So Kepler's third law is the one that's quantitative, and I want to derive that. So here's what it says. Kepler's third law just says that if you've got 2 objects orbiting a common center, let's call one of them object 1 and one of them object 2. The ratios, the square of the ratios of the periods is always equal to the cube of the ratio of the orbital radii. Okay? And I'm going to do 2 things today, and that's really what I want to accomplish. And after that, we can mess around. We'll talk a little more about. I'll get back to flat. There's a couple things I wanted to see. But let's go ahead and.
Wait, no. Just want to write that down real quick.
Okay.
Okay.
Okay. So. Okay, so let's do just a little derivation. And this is just one way. I just did this at lunch today, just as one way to show it. There's other ways to do it too, but I think this maybe not a bad way. So if we use these couple relationships that we know, centripetal. This is really just the law of universal gravitation, right? Little m times a is gravitational force would equal g times big M times little m, but we're going to divide both sides by little m to just get acceleration, right? So centripetal acceleration in this case for uniform circular motion is just g m over r squared, right? Now, we're using the case of uniform circular motion, and we're going to describe elliptical motion, but you're just going to have to trust me that if these equations are going to translate, so it's going to work okay, right? There's a calculus way to derive this that's more legit, but this isn't bad. So if we just remember that orbital velocity equals 2 pi r over t, right? Distance over time. 1 circumference over 1 period would be speed, right? Orbital speed. And if we just kind of flip that around a little bit, if I were just to move the v down there and the t up there and the 2 pi down there, right? We could mess around with that ratio and get something like this. R over v equals t over 2 pi, right? No big deal. Okay, so then we know that centripetal acceleration is v squared over r, so we can make that substitution, right? And then if we multiply, okay, let's flip it. Let's take the reciprocal of both sides. So we flip both of those fractions. So the g goes on the top up here, so it ends up on the bottom, right? Just take the reciprocal of both sides. And now we're going to multiply each side through by r, or r over 1, same thing, right? So if we do that, we end up with r squared over v squared on the left and r cubed over gm on the right. Okay, but remember, r over v, we already determined is t over 2 pi. So we can make that substitution, right? We could turn this into, we could write r squared over v squared as the quantity r over v squared. Everybody agree, just property of exponents. And then r over v becomes, oops, gotta go to the next page, I guess. Becomes t over 2 pi, right? Okay. Let's take these one at a time. So it becomes t over 2 pi, right? R over v. So then we end up with t over 2 pi, quantity squared, equals what we've had on the right for a little bit, r cubed over gm. And then we could write that, we could distribute the exponent to make that t squared over the quantity 2 pi squared, which is 4 times pi squared, right? Okay, now why are the t and the r parts yellow and the others white?
Because those are part of the Kepler's third law.
Okay, but there's something else there that's important. There's another distinction.
Are they?
Well, I mean, no. But look at the stuff that's not yellow. What can you tell me about it?
Constant.
It's constant. Yeah, right? For this situation, it's constant. 4 and pi are constant. G is the universal gravitation constant. And the mass of the gravitational center is not changing, right? We're assuming that we're going to talk about satellites around the Earth or the Sun, right? And that's the comparison we're going to make. So the mass of the gravitational center is going to be fixed, right? We're going to have one gravitational center, and we're going to compare the trajectories of different satellites around it. That's the whole point of Kepler's law. If we go back to here, right? What did this mean? We're talking about object one has an orbit around the satellite with period T1 and radius R1. Object 2, different satellite, has a different period T2 and radius R2. But we can compare those orbital trajectories in this way, right? Okay, so the yellow ones are the variables and everything else is a constant, right? So then if we just divide, well, let's just exchange these diagonally, which is fair math to do when you're talking about a ratio, then look what we get. T squared over r cubed equals a bunch of constants on the other side, which we could just call k. Just a big constant, right? So if that's true, then we could take object 1, that'll be yellow. So T1 squared over R1 cubed equals a constant. Same constant that T2 squared over R2 cubed would equal, right? Just two different orbital trajectories around the same object. And the ratio for a given satellite, the ratio of T squared over R cubed is always going to be a constant, okay? So because they're both equal to the same constant, we can set them equal to each other, right? And then all we got to do here is let's just exchange diagonally, right? Let's just exchange these two terms diagonally. And what do we end up with? Well, if I factor out the powers, I just get T1 over T2. That ratio squared equals the ratio R1 over R2 cubed. You got Kepler's law, right? Okay, Kepler's third law. And that's the one we use the most. So let's try an example. Like here's a problem where we could use that. This is a problem from your upcoming assignment, okay? So an asteroid revolves around the sun. So what's the gravitational center here?
The sun.
The sun is big M, right? Okay, that's important. revolves around the sun with a mean orbital radius 4.35 times that of Earth's. Okay? The period of the asteroid is how many Earth years? Okay, so when we use Kepler's law, one of the two orbital trajectories has to be one where we know both parameters. It's like the reference orbit, right? And the other one's the one we're comparing it to. So in this case, what's providing the reference orbit? The Earth. Yeah, the Earth's journey around the sun is the reference orbit, right? Okay, so, and we are, because we're talking about R, we're assuming that these are circular orbits too, right? The radius is staying the same. So even though Earth's isn't perfectly circular, we're assuming that it is, right? It's very close to being perfectly circular. We'll just do a mean radius for the Earth, and we'll call that R. Okay, so then we know that the Earth we'll let, instead of calling it T1 and T2, why don't we call it T sub E for Earth and T sub A for asteroid, how about? So T sub E is how long in Earth years? One, right? 1 year, okay? What is R sub E? Well, we know what it is, but honestly, do we even need to put that number down, right? Why don't we just say R sub E is 1 AU? We can call it whatever we want to, but the technical term for it is an astronomical unit, which is the distance from the Earth to the sun. But we could just call it 1 Earth radius. That's fine, right? Because if we look at the other, so that's our reference, right? Let's look at the other satellite. The other satellite is an asteroid. And what's its period? Well, that's what we're trying to find, right?
TA.
Oh, it's T, yeah, T sub A, you're right. Okay, that's what we're trying to find. But what is R sub A?
4.35 AU.
Yeah, it's 4.35, in this case AU, but we could even say it's 4.35 times the radius of the Earth, right? You see what I'm saying? Now, in Kepler's law, what are the units of this ratio?
Whatever you need it to be.
Sure, and in the end, they're going to cancel, aren't they? Right? So these are unitless numbers that we're comparing. See what I'm getting at? So then, if we plug this stuff in, right? So let's set up Kepler's law for us. Now, we're trying to solve for T sub A, so let's put that one on top. You always want to put the unknown on top so it's easier to solve for, right? Not a big deal, but it's a little bit helpful. So T sub A over T sub E squared equals R sub A. I don't know why I made a capital R, but I did. Capital R sub A over capital R sub E cubed, right? We could use astronomical units here. That happens to be a perfect unit for us, but pretend it wasn't. We don't even need to. We could make the right side equal 1 R sub E, right? The radius of the Earth is 1 radius of the Earth on the bottom, and on the top we could make that 4.35 Earth radius, right? And what happens? They cancel, right? You see what I'm getting at? So we don't even really need to have a unit here. If we know that by knowing that the asteroid is 4.35 times as far from the sun as the Earth, we know that the ratio of R sub A over R sub E is just 4.35, right? We don't even need units. We're just comparing relative distances anyway, right? So we get this ratio cubed equals, what do we got over here? We've got T sub A over 1 year, right? And we can just the units are gonna cancel anyway, right? We can just get rid of the units. We're just trying to solve for that number. And that's a pretty easy equation to solve. That's squared, right? So we end up with T sub A squared equals 4.35 cubed. So what do I do to both sides? Square root it, which is the same thing as taking both sides to the 1/2 power, right? So if I take both sides to the 1/2 power, what do we end up with? T sub A equals, if I take a power to a power, what's my rule of exponents? Multiply, sure. So I just get 4.35 to the 3/2 power. You can make it a 1.5. You can even make it a decimal if you want, right? So all we have to do here is just pull up, oops, wrong thing, that thing. We just need to pull up our calculator. Use stay put, always in front. All right. So we can just do 4.35 to the 3/2 is just 1.5. So there's my answer, 9.07 to 3 sig figs. Right? So we can go back, and I think this is still on, oh no, I probably got rid of it, didn't I? All right. Well, that's the right answer. So it'd be,
About 9 years.
yeah, so we're looking in years, so it'd be about a little over 9 years is how long that asteroid would take to orbit the sun once. Okay, does that make sense? Okay. We'll go through another example tomorrow. But it's not real hard to use. Okay.
Don't